Exponential decay and half-life. When you're studying exponential functions at some point, possibly in grade 11 or maybe elsewhere, I hope that your teachers are going to go over this concept of half-life, or at least introduce you to it, because it's kind of useful later on if you're studying sciences. Now, what is this half-life all about, and how does it relate to these exponential functions or exponential decay? If you recall, when you have an exponential function, so I'm going to just take kind of a deja vu function, so let's say a b to the x, and we know that this b is between 0 and 1, then our function in general kind of decays. So we will assume for this video that x is greater or equal to 0. So if I'm going to plot this out here, what we will have is that our function is going to start off at some a right here, because that's at x is equal to 0. It's going to start to decay kind of like this. So it's going to proceed, okay, and kind of go in that particular direction. And then the rate of how quickly it's kind of decaying will depend on the size of b. Now, there was another way of writing this in terms of exponential decay, which I personally like a little bit better, and because it highlights the exponential decay in a little more, hopefully, intuitive way, in some way. So instead of writing b, we can transform our b and say that b, so this is b is just 1 minus r, and then r is going to be in between 0 and 1, and r is just some rate of decay, okay? So how quickly something is decaying. So maybe at 5%, 10%, or something else. So you have seen this when I was taking up exponential decay and exponential growth. Maybe I'll put up a link up above there in case you want to go over that. So I'm not going to go over all the details here. This is kind of the introduction of the function that I want to talk about, and then relate it to half-life. This word half-life, all it is in exponential decay is it's a special case for this r that we have in here. So this r, okay, can take on any values between 0 and 1. And for half-life, what it stands at, so it stands at one particular case. So the word half, you probably could guess, basically means 50%. And that's what half-life is all about. So what it is asking us is, what happens when r is equal to 50%? Which really just means 0.5 or a half, and that's where the word half comes from. So if I would plug that in, then my function that I would have would be equal to, so we still have our a, we still have our starting point, whatever it is that we have, and then if I plug in 1 minus the 50%, so let's say 1 minus the half to the x, then what you notice is that this function, well, 1 minus a half is basically a half. That's what you have in here. And this is what highlights the half-life. Half means, okay, so if our base is equal to a half, really what it's asking us is, how quickly our function kind of goes and gets to the half point, okay, of what it has started with. So let's imagine, let's say we have, I'll kind of make this up, but I just want to give you some intuition. So let's imagine that we started off, with, let's say, 64 slices of pizza, okay? So we had 64 pizza slices. And then, someone comes along and says, okay, so with these pizza slices that we would have, so I'm going to kind of put it like this, this is the 64 slices. Someone might say, okay, so how long would it take, for half of the pizza to be gone? So from 64 slices, we basically are interested in, okay, so what happens when it is halved, okay, in some way, Now, I don't know if this is exactly half, but I think you get the point. So this would have been 32 slices, right? And now you can continue this, and then you can say, okay, well, what if we were to take the 32 slices now that we halved from the original, and now we half it again. So now we have 16 slices. All right, so this would be 16. And then we can keep playing this game and say, okay, well, what's half of 16? Okay, well, that's 8. And then it's 4. And then it's 2. And then 1. And so on. And so as you can see, I'm basically halving, okay, constantly at each point in time. So this was 8, 4, okay, and so on. So you can see that you can keep halving it. Now, if I wanted to draw, so if this was my starting point, this right here, I had these points along the way, you can see that really, well, I'm going to do the best I can here. I'm going to try to go through all of these points. But this basically looks like that exponential decaying function. So we would start here. So our A was 64 slices, and we're interested in, okay, so when are we halving that? And then, our X, okay, so maybe instead of using X, I'll use N again. And N just represents, the period of time that it takes to go from 64 to 32. So basically to half that in size. And then from 32 to 16, how long does it take to half that in size? And we're assuming that these time frames are basically identical, that it takes the same amount of time, okay, for this. And if that happens, where those time frames, so we call these time frames, so from here to here, so this time frame, so this is called the half-life, okay, period. Okay, so that T just stands for time. So how much time does it take? And then the half just means, okay, from the original to go in half. And, so this would have been your second half-time period right here. So T, another a half. Now, we can find out what these time frames are. Sometimes people will tell us, or sometimes, the information that is provided to us, okay, tells us, how long does it take to half something. So that's all that half-life is about. So half-life is the concept of an exponential function that you have, and it's a special case where basically, the rate of decay is 50%, which brings things down to a half. And then we want to know, okay, so how long does this take? How many periods would it take to get to a certain point? Okay, so I'll give you another kind of example to relate this back, and because it doesn't really relate back to pizza slices, but I just wanted to make it simple. But where it certainly is related to is, for example, things like radioactivity, okay, so radiation, and then kind of the decaying, okay, constants within, so how much mass maybe some compound has, and maybe it's giving off energy, so it's, the half-life of energy, or half-life of mass, okay, or the half-life of a population. So how quickly something kind of decays, or maybe a virus, right, that we want to be able to see, what's the half-life of a virus? If we started off with 100 cases, when are we going to get to 50 and then 25, okay, and then so on. So we're constantly halving this. So again, so let's imagine, okay, that we started off with certain amount, okay, and I'm going to draw two time frames here to try to relate this back for you. Okay, so this is, I'm going to call this N, which is just the periods. So here we're starting at 0. This is going to be 1 period. This is going to be 2 periods. This is going to be 3 periods. This is going to be 4 periods, okay, 5 periods, and so on. So you can keep going. And for each period, whatever we start with, so whatever this amount might be, okay, so this right here, let's say it's starting point. This is your A. And then what will happen is, okay, so this is going to be, A divided by 2, okay, after just 1 period. And then this, okay, so right here, so again, we're going to half this, and this is going to be A divided by, well, okay, this is going to be 2 squared. And, where is that coming from? So that's coming from our function, so A, right? So this is 1/2 to the N, Okay, so notice when n is equal to 2, so if this was equal to 2, then indeed it would have been a multiplied by 1 over 2 squared, and 1 over 2 squared is just, 1 over 2 squared that you would have. So you can half this continuously, okay, and just keep going. Now obviously this is going to get smaller and smaller, and these halves that I have, this is going to be 2 to the 3, this is going to be a 2 to the 4, and it continues on. Now these are called, so 1, 2, 3, 4, and 5. Okay, n represents, that's the period, and period means time, how much time. Now sometimes we know what that time is, and so I'm going to kind of take this, okay, and let me duplicate this thing right here. I'm going to bring it down, try to relate it back in here, and I just want to show you. So here is your, if this was n, and let's say make this t, that this is actually the actual time that it takes. Now this time t, so this would have been time t0. Now this t would have been, the half period. Okay, so this is the half-life period, okay, of just 1. This would have been, so this right here, this would have been 2 half-life periods, whatever that t is. Maybe t is 3 days or 100 days or something like that. Okay, this is going to be 3 time half periods, and then this is going to be 4 half-life time periods. Okay, and then so on and so on. Okay, so that's what you have. Let's see this in action so that you can see a couple of examples with respect to this half-life. And hopefully those examples are going to illustrate to you, how this function is kind of useful. And then, this halving, okay, that is happening throughout. And then when you finally get into sciences, maybe down the line, and then you see half-life again, you'll be like, oh yeah, I've heard this somewhere. And then hopefully you can relate the two together, and then it will come back to you much faster. If you've never seen it before, then it might be a little bit harder to understand. But overall, it just comes from the fact of having your exponential decaying function where your rate is 50%. Okay, you're just halving the original amount and you're continuing to halve. So here are a couple of examples which are actually pretty relevant. And this is what you would see in sciences sometimes, well, even maybe in math, depending on how your teacher sets this topic up. So a population of 64,000 people have been infected with a virus. If the half-life of infected people is 24 days, then how many half-life periods would it take to decrease the number of people to only 250 infected? How many days would that actually take? And then construct an exponential function for this scenario and graph it. Assume the independent variable is time t. All right, so we're going to try to set this thing up. And then how does it relate back to this half-life? Okay, I'm going to actually start with C. All right, with this constructing an exponential function for this. So in order to answer, okay, part C, now we're talking about a population, so I'm going to say P, okay, and our variable is T, and this is what I'm going to put in here. So we have something, it's supposed to look something like this. A, right, we know that we're talking about half-life, so whenever you would see that word, half-life, that makes your life easier because the B is always going to be 1 over 2, because it is half-life, right? That's 50% reduction. Now, here, okay, so this, what I'm going to be putting in here, in terms of, what does it go up to? So I'm going to put T, okay, so that is the actual time. But remember that the variable, okay, so that T, we need to know, okay, that in terms of half-lives. So I'm going to kind of go back here and say, what if this was the n, and n just represented the number of periods that we would carry? Okay, so now this n, what does this actually equal? So if I go back in here, remember that, so this is your n, your n is 1, 2, 3, 4, and so on. And then here, this is your time periods. So for this example, they told us actually that the half-life is 24 days. So what this means is that this is actually 24 days, okay? Twice that much is 48 days, okay? And then so on. So this is what we have. So what does that tell us about n? That n is equal to, okay, how many days you have divided by your half-life. That's what n actually equals. And if I'm going to set this up, so this is going to be n is equal to t divided by, for our case, which is 24 days. So t is going to be in days, right? So that's the independent variable. And notice, when we get to 24 days, 24 divided by 24 is 1. And that's when you would be at the half point. Now, if you get to 48 days, so notice 48 days divided by 24 is going to be 2. And that means you again half, okay, the previous amount. And then you continue on. So the setup here for the exponential function, if somebody actually tells you what the half-life is, you can set it up in this way. So I'm going to do that. So instead of writing here the n, now my n is equal to t, which is in days, divided by 24, which is your half-life period. So what do I have? I have this a. Now my a, what am I starting with? I'm starting with 64,000 people. I have 1 over 2, that's my half-life. And my t, or my n, is really just t all over 24. So that's how you can set this up if you wanted to have it as a function of t. Now another way of doing it is that sometimes, you might want to write it as n. So your population, okay, as n, it would have been 64. Now this one is simpler, but it's exactly the same thing. So here, this would have been n, okay, like this. And this just tells you how many periods it takes, right? That n is actually in terms of time, and we know it in this case, and it's this. So let's plot it so that you can see, okay, so how this is actually progressing. So I'm going to take out Desmos. All right, so welcome back. So I wanted to set this up kind of in two different ways. All right, so as you can see, so I put P of t, which is with respect to time, and then I put G of n, which really just means the population. I just didn't want to have two P's, okay, as my functions. So that n just represents the number of periods, okay, that it would take. So notice I first plotted, okay, just with respect to n. So if you're going to start, okay, so right here, okay, you're starting at 64,000. Now after one period, so at 1, so if I would plot, okay, so this, and I would keep going in here. So what you would see is I'm going to plot, okay, so 1 and then 32,000, 1, 2, 3. Notice that is exactly the half point, right? So that's the half, at half-life at one period, okay, it got halved. And now, so I can continue this. I'm going to put a comma. At 2, well, it's going to be half of the 32, which is going to be 16,000. Okay, and notice that that's that point. Now, again, I can, at period number 3, so what's going to happen, this is going to be at 8,000. 1, 2, 3. Okay, I'm going to just label these so that you can have it and you can see that those are actually the half-life points that we have along the way. So that's one way of graphing it when it's with respect to n, and n represents the number of periods that you have. Now, if you recall, in the question, they actually, part A, they said, how many half-life periods would it take to decrease the number of people, okay, only 250 infected? So if I wanted to see that within here, so let me plot this, because what I want to see is, okay, at 250, so that's the intersection, right, between the two graphs. how many half-life periods would that be? I mean, I can squeeze in here and just keep going. Okay, so just to see where they're intersecting here. So here's the intersection point somewhere here, and notice, okay, that's 250, and that happens at the 8th period. So that's when it happens. Now, what does that actually mean? So how many days would that take? So that's part B. So how many days would this take? Well, if n is equal to 8 periods, now don't forget n is equal to your time in days divided by 24, and where 24 is the amount of time that it actually takes, right, to half your population of the virus. So if I'm going to solve this equation, so this is not a very hard equation to solve, so t is 8 times 24, and there you have it. So, you can just say, all right, so 8 times 24, and that's going to be 192 days that it actually takes. But how many periods is that? Well, that is 8 periods, right? 8 half-life periods. So that would have answered this particular question. Now, I do want to go back in here, and I'm going to, so within here, so let me kind of take these things out, but instead, let's plot the actual result with respect to, so I'm going to kind of take it like this, and now let's remove those plots. Now my t is with respect to time. So this is the population with respect to time. So what should we expect for this? Well, we should expect, okay, so if you're going to be starting at 64,000, your first half-life, right, is 32,000. When does that happen? In 24 days. So in 24 days, so if I keep going in here and I, try to plot this along, so let's try to get to 24. So 24, where's that? 24, there we have it. Okay, you see that on the screen. So after 24 days, notice it's 32,000, which makes sense, right? Because t, which is 24, divided by 24 is 1, which is 1 half-life period. So the next one, the 16,000, okay, so if I keep going, that would have been at 48 days. Okay, so let me go back here to 48. There it is. So 48 days is 16,000. And now you can, continue. So now we're going to get into 8,000, right? So 8,000 was our next one. So where's 8,000 here? And how many days would that be? Well, it's an additional, okay, so there we go. We just passed it. Okay, so 72 days, which makes sense because it's 3 times 24. So this graph is with respect to time, and our previous one was with respect to just periods, and you can graph either or, and you can use the exponential decaying function for that. That's one example that you can see with respect to this half-life. Here's another half-life example. Here's like a tumor example. So there's a tumor of size 464 grams, and it's decaying at a half-life of 82 minutes. So maybe it's being, whatever is happening, so it's some kind of a tumor, we don't know, but it's decreasing in size. So, we're going to have this tumor, okay, right here, it's 464 grams, okay, and then in 82 minutes, what's going to happen is going to be half of that size, okay, so half of that size, it would have been, 232 grams. And then again, after another 82 minutes, what will happen is, okay, it's going to be half of that. Okay, so meaning it's going to be 16, okay, grams. So that's the half-life period. And this, okay, so this is after 1 period. This is after 2 periods. All right, so right away we know, okay, so what do we know? We know that our starting point is 464 grams. We know because it's with respect to half-life. So what that is telling us that n is equal to, so in this case they give us what the half-life time is, so that would have been 82. But in this case t represents, or t, the units, okay, for this is minutes. In the previous case, it was days. So that is important because obviously days and minutes are different. So that's how we would set this up. So this 82 that you see, this is your time for one half-life to occur. And once we have this, then we actually have the entire function. So now this is tumor and its mass. So I'm going to put m, and I'll put it in with respect to t. So we have that. And then here, so what we have, we're starting with 464. It's half-life, so this is always half. And this is going to be t divided by 82, if you want to write it with respect to time. If you want to write it with respect to just periods, which we typically write as n, it would have been the same. So it would have looked almost identical, except you would write it like this, if you're just interested in how many periods it has. So both of these are fine, but they're with respect to different independent variables in some way. Now the variables are actually dependent on each other, so n and t, so because n is equal to t over 82. Now I haven't even read the rest of the question. It says construct an exponential function modeling this. Well, okay, so there you have it. So we've just modeled it. So that's what we have there. And what independent variable are you using? Well, I guess you can use either or. So here you can use the independent variable as t, time in minutes, or you can use n, which is periods, so number of periods, half-life periods. And what else do they ask? What is the dependent variable? Okay, so the dependent variable in this case, because this is a tumor in grams, so the dependent variable is going to be mass, right? Because we measure mass in grams, and then the units is grams. Graph the exponential function and identify how long it would take to reach a size of less than 1 gram in size. So how long? So if they say how long, I'm assuming it's time. Okay, so how long? So let's take a look and let's graph this out. So I'm going to graph it with respect to time. I'm going to put it at 1 gram. And then, you're going to see kind of this decaying. So let me put in another one in here. I'm going to put m of t is equal to, and we're starting with 464. I guess it's 1 over 2. And this is to t all over, this was 82 minutes. All right, so this is what we have. And I'm going to put a restriction, so t is greater or equal to 0 for our function. So this is what we have. So we obviously have to zoom in here because, so that's my starting point. So notice 464. And now after every 82 minutes, it's going to half. And now, so what I want is, I'm going to put y, okay, just for the vertical axes, y is equal to 1, okay? So I want to see when it crosses that, right? When does that happen? So I'm going to do that, okay? So there we have it. So there is 1. So obviously this is going to happen, much later, okay? So there it is, okay? So that's that intersection. So it crosses it at approximately 726 minutes, right? So it's a little bit more. So let's say 727, because it says I think it says less than 1 gram. Less than 1 gram. But that's what you would do. You would just put your, flat line, intersect it with your exponential decaying function, and then you can see exactly when that happens. So that mass just keeps decaying, and gets smaller and smaller. So that's how long it would take. Now, if they asked you how many periods that was, well, then you would take the amount of time that you have. So if I go back here, if I plot this back up, so you would just take the amount of time that you carried. So it was, I don't know, was it 726? Okay, so 726, I'll put 0.4 or something because it's less than 1. And now I know that the time, okay, each period is 82 minutes. So if I divide it by 82, so it's approximately, 8.9 periods, or almost 9 periods it would take for this to go under 1 gram. So that's an application that you have of half-lives. All right. Okay, so thanks for watching. I hope that this was useful, and for those who did watch it, especially those in grade 11, you know, it might help you down the line when you are studying these. I know that in healthcare, they like to study cases like this. In chemistry, they like to study cases like this, so half-life does pop up, and now you hopefully will know a little bit about it. Okay, bye everyone.